4.5 is on optimization. So applying some of the techniques we've been doing for actual application. So let's take a look at this one. I already have the picture that was in the book as well here, but we'll draw it as we go as well. So a long rectangular sheet of metal, 12 inches wide, is to be made into a rain gutter by turning up two sides that are perpendicular. So you could picture a sheet of something, and then you're going to bend it up right here and here, and bend it up so you create this trough, basically. Okay. How many inches should be turned up to give the gutter its greatest capacity? So we're looking at basically a cross section of that. So we want to think of it like this. You have a 12-inch piece of like a sheet of metal, right? So this would continue on this direction. So you have this sheet of metal like this, and it keeps on going. So I'm not gonna. So it's kind of chopped off there, and then you're going to bend it up. You're going to bend up. You're going to take somewhere in here and here maybe, and it's assumed to be equal, and you're going to bend it up right there. So when you do that, you get something that's going to look more like this. And so here's your rain gutter. Looks going to be something like that. Just close to that anyway. Okay, and so, and then it goes back here as well. Actually, I could copy that. I could just paste it again, can't I? So it goes here, and we'll make this one dotted down here. So that's essentially what it's going to be. And this is chopped off here and back here. And so that's open. That's really nothing there. What I wanted to do was make these dotted back here. Like that. So, and that's what the picture is on the side. So originally you have this whole piece is 12, right? This goes from here to here. That's 12 inches, like that. And so when you cut it, you're going to cut it some amount equally. So we're going to call that value x. So this height then is x here and here when you cut it off. And so we don't know what this piece is right here. I'll just call it z. But you know the total length is 12. So what you're doing then is you're taking this length of total of 12 like this, and cutting it here and here the same length of, say, x and x. So then you get the middle part then would have to be 12 minus 2x. Okay, so there's your algebra step. And that's what we have, of course, right here is 12 minus 2x, where these are your heights, your x. All right, so now what we're looking at then for greatest capacity, the capacity of this stuff running through it. So you have your water basically running through this here. Your greatest capacity is going to occur, so it's going here, right? When your cross section is the largest. We want to maximize the cross section. Cross-sectional area. So we're going to maximize the cross-sectional area is what our goal is going to be. So you need to set up that function. So that function f of x will equal, well, then you just look at this. You have this distance times this height, right? That gives you that cross-sectional area, which is this. So z times x, and then z is, of course, just the 12 minus x. So the cross-sectional area is zx, or 12 minus 2x times x. And so when you distribute that, you get 12x you get 12x minus 2x squared. And so we may want to think of that as, now you're thinking this in terms of a function, like that you're just interpreting this mathematically, not the, right now, not the trough thing or the rain gutter. So what type of function is that? What is this thing here? Okay, so we know that's a parabola that opens upside down, so there is a local maximum right there. And that has to be the local max, because we know that that's what the picture would look like. And we also know it goes to the origin, so f of 0 is 0, which makes sense. You have no height, well, then you'd get no area. Okay, so this is really an area function. Sometimes I'll call that a of x. Right, so we know that this is a parabola that, let's try that again. We know this is a parabola, and we know it goes through the origin. It's upside down. So we know it does something like this. Okay, so it goes to the origin. So there is going to be some height, like right here. We don't know what that is. So we'll call that value x naught or c or whatever you want in there. So that's what you do. You find the extrema of that. So find extrema. And so we set f prime of x equal to 0 and solve. So take the derivative, f prime equal to 12 minus 4x, set that equal to 0 and solve. Right, so you can see that's just 3. X is equal to 3. And for this one, it's pretty simple. You can just do the second derivative. And then we can get that you can test to make sure it's a local maximum. Second derivative is just negative 4, which is less than 0. So that implies concavity like that, which we already know because of the graph. So therefore, x equal to 3, which is a critical value, right? That's our CV. And it's always concave down, so that critical value must be a local max. So it is we'll just say maximum. And it's a local max, but it's also absolute maximum. Okay. All right, so given that, then, to answer the question, so the question was, fix that, how many inches should be turned up to give the gutter its maximum capacity? So you turn up the sides at 3 inches, or something like that, for maximum capacity. Okay, so that's the concept. There's a lot of things in here we're going to go over in terms of guidelines. We have some things in terms of the function. You create some sort of function, and we find the extrema of the function. We'll talk about keeping it in the domain of the function. So one of the things for domain here, we could talk right now, really, that x has to be basically what has to be between 0 to 6. So that's one of our domain concepts that we can discuss. So it has to be 0 to 6. So it can't be 6. You're folding it up the whole half of it. There's no area there. So this is a domain idea that we need to think about. Then we maximize. You don't have to do a second derivative necessarily, but it makes it really easy with a polynomial, right, to get the maximum value. Okay, so we'll look at a number of examples from here. Next, let's talk about just some basic guidelines for solving optimizations. Okay, so we'll just call this guidelines. For solving optimization problems. Okay, so number one, read the problem. Sorry about that, I'm back. Okay, so guidelines number one for optimization. Number one, read more than once. I'll kind of abbreviate what's in the book and my own things in here too. So you read more than once. As you're reading it, what I want you to do is think about given facts and unknowns. Okay, two. So you read it through once and you're thinking about what are the given facts, what are the unknown variables, that kind of stuff. Number two is sketch or diagram. So anytime you can sketch a diagram, you need to do that. You want to get a visual depiction of what's going on. And then you want to start labeling or label the diagram. And at the same time, define variables. So we did that back here, right? We sketched it, right? What's going on. This one was given, but it's usually not going to be given. You want to sketch what's going on. You start labeling different things. So first I said it was Z, but then I made it and I figured out what that had to be, right? That kind of stuff. Okay. Number three, write down known facts and relationships. So write down like area of a circle, that kind of stuff. So write down known facts and relationships. So how one variable is related to the other, is one 2 times the other, that kind of stuff. Number four, determine which variable to be maximized or minimized. Okay, so this is another kind of a tough step. Determine which variable to be maximized or minimized. Express the function as one variable. So then you want to express the function as one variable. So you are using the relationships between the variables above to say it's just a function of, say, x or maybe h of t or something like that. That's your next step. 5, find critical values. For f prime, f double prime. I'll put back here, consider domain of the function. So what's the domain of your variables? Okay, determine extrema. All right, so now you do your extreme test just like you normally would for a function f. Check endpoints if necessary. If they exist. So it could be that you don't cut it at all or something, that kind of thing. So check endpoints on domain if it exists. I'll put that down here, if exists. It may not. And then after all that, ask the question, does this make sense? And then 8, answer in a sentence. So, but I'm going to focus on 7 for a second. Does this make sense? So you don't want to get like, a turtle that's running at or walking at 5,000 miles per hour. That just would make sense. So you want to make sure whatever you're getting makes sense. If you're talking about area, can't be negative, that kind of stuff. Okay, we will go on to a number of examples now, and we'll apply these steps. This isn't really a linear process, right? It doesn't go from 1 to 8. I mean, you're thinking through the whole thing as you go. It's kind of in this order, but it's more like that. Okay, more to come.